Ah, okay. Okay.
You can start
I
again.
don't have to start again, right?
Yeah, you should say that I'm moving part.
So indeed, like, of course, we know we have a very good framework to describe interactions and so on, up to the scale of activity EV. And of course, we have the Planck scale here, and we can ask what's next. And because we have gravity, and the CFT must be coupled to quantum gravity, the big goal in this whole Swampland program, so on, is simply to try to explore and understand some generic properties of quantum gravity, and in particular with the goal of trying to eventually connect and constrain low energy physics. Now, the way we typically go about it is because we have a quantum gravity framework, string theory. I'm here showing only like supersymmetric string theories, but the point is that we have this framework, it is consistent, and we can use it to try to see patterns. Now, the criticism to this sometimes was that, okay, I have this bunch of theories only in 10 dimensions. Then I also have my non-supersymmetric ones. Then I can compactify them, and I can have a bunch of low energy EFTs. There's these famous numbers that probably you heard of, these 10 to the 500 and so on and so forth. And this was used as a criticism in the sense of, okay, you have this framework, fine, but you have so many things that you can accommodate there that basically anything can probably be accommodated, right? And this is this idea of the string landscape, namely the effective theories that can be obtained from a string theory covering basically every low energy EFT. Now, as opposed to this, the idea of the Swampland and what we have observed in recent years is that indeed, even though this landscape can be very large, there is also a set of consistent like EFTs that look consistent in the IR that cannot be coupled to quantum gravity. And what we are trying to do is to ask what are the general features of these quantum gravity EFTs. And in particular, the way in which we go about it is we try to see patterns and we conjecture about these patterns. So we see a pattern and we try to check if from the information we have, namely string theory, so on and so forth, if this pattern actually makes sense, if it has to be, I mean, if it's true for all quantum gravity theories, if it's not, if we have to refine it. And indeed, you can see that there is a bunch of conjectures. And at this point, I saw this in a presentation from Oguri, and he put them in this so-called main sequence of conjectures, where this useless useful means useless or useful to try to constrain low energy physics. And this rigorous or speculative has to do with the amount of evidence that we have to for these conjectures. Sadly, we have no giants here. We would love to have giants. We are trying to push some of these things to evolve into giants. But this is just to give you an idea of the fact that we're just trying to see what are these patterns. And some of them we know are more robust statements. Some of them we know are less robust, but we're just trying to understand what's behind them.
But sorry, so that suggests that all rigorous results are useless?
So as I'm going to try to comment, when I say useless, I mean to constrain low energy physics. So most of these conjectures, like no absence of global symmetries, absence of free parameters, at this point, they cannot really constrain low energy physics in a straightforward way, because usually they come, like the price we pay is that we cannot bound the energy scales at which these things have to have impact. Therefore, I can only say, well, I will go into no global symmetries in a minute. I can only say there must be no global symmetries, but I cannot tell you at this scale. This is what somehow needs to be added to make them more useful in this sense. Now, I'm not going to go through all of this. As I told you, the goal is to explore and understand this, but I'm not going to explore all of them today. But just to recap, the general strategy, as I mentioned, is to combine lessons from top-down construction. So we have string theory, or we have AdS CFT, with bottom-up constructions, namely black hole physics or unitarity of causality of gravitational amplitudes, things like that. And additionally, we try to find interrelations among them, And what we have observed also over the last years is that many of these conjectures are indeed interrelated. So if you basically kill one of them, you could kill many of them. So this gives some internal consistency. And then, of course, you can just assume them and see if the constraints they provide are sensible. Because if I give you a conjecture and I tell you the standard model violates it, then it better be wrong. So I think all these approaches are very interesting and complementary, and I personally have like to work on all of them. But today, I'm going to focus on black hole physics. Now, the point with these kind of black hole physics arguments is that they are more general than taking a particular class of string compactifications or a particular family of CFTs or things like that. But of course, even though they are more general, the price to pay is that we cannot be so precise. So these are usually taken as motivations or insights, as I was highlighting in the title, to guide us through what things could actually be this part of these fundamental properties of low energy gravitational EFTs. And then once we have these ideas or these insights from these, we can combine them with top-down or interrelations and so on. So the plan for the rest of the talk, I try to motivate and summarize a little bit this Swampland philosophy, let's say, approach to quantum gravity. What I'm going to do is I'm going to start with a very brief recap of indeed no global symmetries and how this was motivated from black hole arguments. Then I will go to the main part of the talk, where I'm going to talk about the distance conjecture and the relation between minimal black holes and tower of states. And finally, if I have time, if I don't, then we can skip this part, but I hope I have time. We will talk about scale separation, the AdS distance conjecture, and I will tell how these two are related, and how black hole transitions can also help us understand this a little bit better. So let me go to the first part. So no global symmetries in quantum gravity. Just for you to get a flavor of how these black hole arguments work, the first Swampland conjecture that actually predates the Swampland, of course, is that there are no exact global symmetries in a quantum gravity theory coupled to a finite number of degrees of freedom. So if we have a global symmetry, I mean, of course we have global symmetries in it. We have P and L and that are broken by non-perturbative effects in the standard model, and we still have B minus L. So the only thing we're saying here is that indeed these global symmetries have to be broken or gauged at some scale. The reason why this is useless, coming back to your question, is I cannot say exactly at which scale. So if I tell you that B minus L is broken at just below the Planck scale, I cannot constrain much just with that.
What does the phrase finite number of degrees of freedom mean then?
Well, in this particular case, and everything I do here, I just mean that we have an Einstein gravity coupled to a finite number of degrees of freedom, of course, so that I can have a weak coupling limit. I will actually go a bit more into the details of this when I go to the distance conjecture, which indeed we will start having an arbitrarily high number of degrees of freedom and so on. But this is basically to exclude, because actually some of these conjectures are not true, in some like Vasiliev theories or things like that that may have arbitrarily high number.
But is there a scale in the finite number? I mean, are you talking about light degrees of freedom?
Yes. I should say absolutely. A finite, let's say, what I'm saying is that below a finite mass scale, I can never have an infinite number of degrees of freedom. Below a finite mass scale, below the Planck scale, I can never have an infinite number of degrees of freedom. And if I do, then I should adjust the cutoff. And actually, what we will see in a bit is that indeed, these limits have to just be taken with a little bit of care. But basically, this is just to mean that I have weakly coupled Einstein gravity as the limit of my EFT.
What's the worst thing can happen? There's a global symmetry.
Well, I will just, right now, I will tell you something that can go wrong with a black hole.
Okay.
So, and then we can try to think about what's the worst thing that can happen. But the point is that I'm going to try to argue that there is an inconsistency. Black hole thermodynamics is wrong in the following sense. So, first is that. So the heuristic argument in terms of black holes for this conjecture, actually, I'm going to take as an example a global SU2. I won't take U1 just to avoid talking about reference, but this, like, for what I want to tell you, this is more like. So consider I have a global SU2. And then we know that particles transform in unitary representations equal by J. So total J, and the Hilbert space, standard representation, is 2J plus 1. And then if I have one such particle with some J in my spectrum, then I can just make a black hole, a very, very large black hole with a very, very large mass and a very, very large J. And then I start with this black hole. And I let this black hole fucking radiate. I know that this black hole has some entropy that has to do with its mass, and because its radius is also related to its mass, and just let it evaporate. And then because this is a global symmetry, it won't lose charge. Because basically the fact that it's a symmetry tells me that I can emit any kind of J. So on average, it won't lose charge, it will lose mass. And then you can already see that because we were saying that the dimension of this Hilbert space, if I have very large J, is 2J plus 1, but this keeps going down, the entropy keeps going down, and at some point, I don't need to approach Planck scales or anything like that if I have sufficiently large J. So this can be a perfectly valid semi-classical black hole, but still what I will find is that the entropy of the black hole is such that it is smaller than the dimension of the Hilbert space associated to this. So the black hole cannot accommodate the entropy associated only to the SU2, global SU2 part of this solution. And therefore I find a contradiction. What I'm finding is that indeed something is going wrong because my black hole thermodynamics should not be working here.
Contradicted to what?
Contradiction between black hole thermodynamics, so the entropy.
Black hole thermodynamics has to be true.
Well, I think this is probably at the level of semi-classical gravity and all of our understanding of quantum gravity. In particular in this regime, because I'm not talking about very small black holes close to Planckian or anything like that.
Do we have experimental evidence that this has to be true?
Well, we only very recently detected the black holes through gravitational waves, right? So I would say this is one of the most solid theoretically established principles, but I don't think black hole thermodynamics have ever been
okay, so this is the worst can go wrong.
Yeah, like
okay.
If you're willing to give up on black hole thermodynamics, then no contradiction at this level.
Okay, but this is the worst can go wrong.
To me, this is the worst that could go that I can think of that could go wrong. I think indeed. I mean, also like from what we know of UVC, like one of the great successes of string theory is indeed actually giving a microscopic interpretation for certain black holes in terms of fundamental degrees of freedom. So we also have a microscopic interpretation for black hole thermodynamics or for black hole entropy in some particular cases in which we can compute in quantum gravity theory, so in string theory. But let's say if you accept giving up on black hole thermodynamics, I have nothing to. I mean, I cannot say there is a contradiction. Yes.
Just to make sure. So here your R prime horizon is now like, so when you are comparing the last inequality, you're in the region where it's like, suppressed by Planck scale, right?
No, I don't need to. I can just start with a very, very large black hole. Okay. The only point is I need to have a large enough J. But if I have a particle with J in my spectrum, I can just build this black hole with a very large J with an extremely large mass, and I just wait for it to lose enough mass so that I find myself in this situation. It can still be very, very large, like very, very large, like the radius can be very, it will be much smaller than this.
I see.
But it can still be like way above Planckian.
I see. So you're.
I mean, I would really need a very, very large J, because of course this is measured in Planck units and so on and so forth.
So this is still the region where you can trust Wittgenstein.
Absolutely.
In the electromagnetic case, which would be presumably an example of charge, I mean, then if there are charged fields, it would discharge, and if there are no charged fields, then it would stop evaporating. So
So the point is precisely if this were a gauge symmetry, then this process, because I have photons that can detect this, indeed this black hole would discharge, and then I would not run into this contradiction. So the point here, what is important here is that indeed I have a global SU2, because then I can argue that Hawking evaporation is blind to this J, and then I keep the same J. Whereas indeed, like in QED, like a Reisner-Nordstrom black hole, if I did the same computation, I would see that indeed this loses charge along the way, and I find no contradiction a priori.
Right, but I mean, why can't the same thing happen with the global charge of the evaporation stopping?
Okay, so what you want to do is to stop this evaporation at the point at which this would reach this threshold.
Yeah, at there or even before, possibly.
Yeah, I mean, then, but then you would have to tell me why Hawking's computation is wrong in
Well,
a
if the
regime.
surface
in which it
gravity is going to
perfectly-
zero, then.
No, here the surface gravity is, I mean, this is really from the outside, they just see it as a Schwarzschild black hole.
Okay,
So this is really a Schwarzschild black hole. I know it has some J because I built it by doing the J, but from the outside, I cannot measure it.
yeah, okay,
So indeed, that is where because if I could measure it, then I would have some gauge field associated to it to measure it from the outside, and then everything you're saying would indeed go on, and no contradiction at this level.
I have a related question. Is
Yes.
it in principle possible to introduce the interaction between gravity and a charged particles so that, like in a gauge field, a gauge case, somehow a charge loss occurs? Is that considered impossible?
Sorry, I don't know if I'm understood. So you're saying that indeed, if I,
Imagine that you introduce some interaction between the gravity and maybe not even beyond Einstein gravity, but introduce coupling between the gravity and a charged particle, such as a global charged particle, such as fermion scalar. Is it in principle possible to let the charge loss occur via that interaction?
yeah. So what you're saying is I have this charge. I introduce some kind of coupling between this charge, like which is not by gauging the symmetry, but you want to couple it through something
Yes,
like
some
with a-
interaction.
with a
Yes.
scale.
Uh-huh.
But then, I mean, then my question would be if by doing that, I mean, because if this loses the charge and you're not gauging it, then you're breaking the symmetry somehow. Because you're saying that there is a preference from, if I compute the amplitude from emitting some state with angular momentum with latitude J with respect to a different one, then the amplitude is different. And then when having the symmetry is telling me is that indeed, when I transform one into the other, there should be no difference. So then what you're describing, I would put it in general, at this level, into some kind of breaking of the symmetry. But in any case, I mean, also like, I'm very happy to keep discussing this example also, like as much as you want, but this is basically, I mean, it is in general true that all these black hole arguments indeed, they give you a hint of what can go wrong, how it can go wrong. And then what you have to do is like, once you have these ideas, then you have to really try to test it and try to break it and see whether it actually makes sense or not. But here, because we are in the regime in which Einstein gravity and Hawking's computation are valid as far as we know, again, we're not approaching Planckian distances or anything like that, then there is no reason to stop this evaporation before the contradiction is obtained. Therefore, the mechanism is to eliminate the global charge. One can play a similar version of this with a U1 global charge, then one would have to resort to remnants and so on and so forth. But this is like the simplest instance of black hole argument for, well, I don't like to call this one Swampland conjecture because as I said, it even predates the Swampland. So quantum gravity conjecture. Okay, then let me go to the main point, which is the distance conjecture, tower of states, and minimal black holes. So what I'm going to try to do now is I'm going to first introduce the distance conjecture, the towers, and this notion of species scale. Then I will mention, because with this, I will try to basically motivate considering minimal black holes as ensembles of species. And then we will see how using gravitational bounds on entropy and gravitational collapse, one can use field theory computation to understand the scaling of the entropy of black holes in a particular limit going through this black tower course. So hopefully by the end of this part, what I mean by this will be a bit. So the distance conjecture is also one of the most tested Swampland conjectures all over string compactifications and so on. And it basically says that in a theory of quantum gravity, we have a modular space, so we have some scalar field space with no potential in which we can move freely. And we have the theory defined at some point, P. And then I go to another point of this field space, Q, an infinite distance away. Then as I move to that point, an infinite tower of states become massless in Planck units, it's important, exponentially with this distance. What this is telling me, if this is true, is that basically there is a regime of validity for my EFT, that I can just use the same EFT all over modular space. And this in contrast.
Why does it have to be infinite number of states?
Say it again.
Why does it have to be infinite number?
This is the conjecture. This is what we observe in all the examples. And then, I mean, the point with this conjecture is indeed that there is no clear black hole argument, for example, for it. But what we see is that in all string compactifications that we know of, this is the case. We not only have one state, but we really have an infinite number of them. And this is deeply rooted in dualities and things like that. So it's non-trivial at the level of string theory, because it really makes what does the heavy lifting for you in most of these examples are string dualities. But why has it, so
I see that.
this is a pattern that we observe in string compactifications. This is where this conjecture comes from.
I see the appearance of the word infinite twice. So infinite distance, infinite tower. What happened? Finite distance is.
Well, you can have basically what you see is that in these modular spaces, you can have singularities that are at infinite distance or at finite distance. What you find at finite distance is a finite number of states that become massless. An infinite number of states is indeed linked to infinite distances. And actually, the simplest example of this is just circle compactification. You have a circle compactification and you have your low energy FT, you have some supersymmetry just to keep them radium and modulus. Then if you go to infinite distance, that you can compute it's infinite from the kinetic term of the radium, and go to infinite, radius going to infinite, so you decompactify. This tower of states is given by the Kaluza plane tower. If you go to radius equal to 0, actually, what happens is that if you do it in your EFT, you cannot go to very small radii, because you would find the cutoff of your theory. If you have the UV theory, if you have string theory to give us the result here, what one actually finds is that this is dual to this, and there is another tower, the winding tower, that is giving us this infinite distance tower that becomes massless with the exponential dependence in distance. And actually, this already gives a hint of how extended objects play a role in all these conjectures for quantum gravity. But furthermore, what we have observed, again, in all string compactifications, that has been conjectured to be the case, is that these towers, these infinite towers, are indeed always of two kinds. Either Kaluza-Klein towers, so they are basically signaling some decompactification, or the degrees of freedom of a weakly coupled fundamental string. Now, this is something that we're gonna keep in mind for the rest of the talk. And now the other concept that I want to introduce is this of the species scale, because as we were saying before, we have large number of degrees of freedom that become very light, and we would like to have some way to quantify the breaking of the effective theory as we approach this. And now this species scale was proposed originally by these people as the actual cutoff, the upper bound for the gravitational cutoff in a theory with light species. So if I just give you Einstein gravity with a few degrees of freedom, you would expect the cutoff to be at the order of the Planck scale. Now, it turns out you can motivate this from, again, perturbative computations, from black hole physics, or from string compactifications, where we have the UV completion, that indeed, in the presence of an arbitrarily high number of light species that I label here NSP, then the true cutoff can be parametrically below the Planck scale. Now, this, of course, in this context of the distance conjecture, when I have these infinite towers that are becoming light, becomes particularly important. Now, the idea is that then if I have these towers and I can parameterize them by I have some mass scale associated to the towers, and I have some degeneracy associated to the towers that I can parameterize by some P, For example, if I am decompactifying p dimensions, I could parameterize it like this. Then what this gives me is just a relation between the mass of the towers and the number of species and the species scale itself. So I can basically trade one for the other and solve for one of the other when these towers are of KK or string oscillators. I don't want to, I mean, we don't need to have the details. The key point is that this kind of parametrization and this kind of relation really captures the two cases from this emergent string conjecture. The fact that these two towers, KK towers or emergent string towers, can be the light ones. And then actually what happens, I mean, I just told you this, I just gave you this formula and I told you this can be motivated, whatever. But then you could say, okay, this can be very well motivated from the bottom up. It turns out, at least to me, the most interesting piece of evidence for this is that actually in these two kinds of limits that I was telling you about, this actually captures what we would expect. What is what we would expect? What we would expect is that when we decompactify, we have our lower dimensional Planck mass, but we have our higher dimensional Planck mass. And the higher dimensional Planck mass is much smaller, and actually this is what the species scale, when you introduce the KK tower here, is capturing for you. Similarly, in weakly coupled string limits, we would expect the true cutoff to be at the string scale, which as we go to arbitrary weak coupling is well below the Planck scale. And again, the species scale is capturing this. So when I say species scale close to infinite distance limits, actually what I always have in the back of my mind is just higher dimensional Planck mass or string scale. And the interesting thing is that if I consider this as the maximum energy or the minimum length that I can probe, and I plug this in the black hole entropy formula, namely, if I consider what would be the smallest semi-classical black hole, the entropy of this guy actually scales like the number of species. This is just like the simplest thing you can do, and we know the black hole entropy. We can just play with this, and I can just rewrite it in terms of the number of species. So the picture that one kind of has in mind is we have this modular space, we go to this, let's say this is the infinite distance point, an infinite number of states is becoming lighter and lighter and lighter as I approach this. And at this point, at some point, I have a minimum black hole, which is given by species scale at that point. And as I keep going further and further, I have a larger black hole, which is still the minimum one that I can have at that. And for each of these points, these have an entropy that somehow resembles what would be a system of n species at each of these points. So all these things change with moduli, but what this gives you is the idea, okay, the black hole entropy part, I mean, again, in our semi-classical approximation up to the cutoff, I understand the scaling of this entropy. Can I really understand this for the minimal black hole as the entropy of this system of species? This is the question that we want to ask. And to do that, we have to keep in mind two things. So let's now try to consider these systems of species and the thermodynamics of these systems of species. If I have gravity, I have two important restrictions on these configurations. The first one is that if I have a system of free species that I raise their temperature, at some point they will collapse. This can be estimated by saying that the size of the box where I have my species has to be greater than the corresponding Schwarzschild radius. Similarly, we have entropy bounds, covariant entropy bound in more general form, that also tell me that the maximum entropy that I can accommodate in a region of space-time is bounded by the black hole of that size. So it grows with the area. But we know that the entropy of this species grows with volume. So is there any limit in which we can actually understand the entropy of this ensemble of species and it approaches this area law? These two things can be seen as upper bounds on the energy of the system, for example. And the point is that what is somehow protecting you from violating this covariant entropy bound is that if I consider a box of species at some temperature and some length, and I just keep heating it up, I will always reach this point before I reach this point. And what happens at this point, this collapses into a black hole of the same size, but the entropy jumps. If the entropy jumps, I cannot learn much about the entropy of this guy from the entropy of these guys. Now the question is there any limit in which I can approach the entropy of this black hole from a box of species so that I can try to learn something about its scaling. Namely, is there any way in which I can recover the area law for black holes from this system of species? These are the two questions that we basically want to ask if there is a limiting behavior of this box of species as the black hole. And the hint to understand this is that indeed these two guys coincide when I have temperatures of the order of the inverse of the length of the box. So what we're trying to do is to understand simply like the thermodynamics of free species, and free species because I will be close to infinite distance points, close to these asymptotic regimes, and see how indeed we can get the volume dependence of this entropy in some limit and the area dependence of this entropy some other. So as I said, I consider a box of particles in a box of size L with some spectrum, and I can neglect the interactions because I am close to these infinite distance points. Therefore, I am at temperatures below the cutoff, which are much smaller than the Planck scale. Again, of course, if we wanted to do a detailed analysis of this, we would need to consider all the back reaction and so on. This is beyond the limits of our EFT. We would need some other arguments, but at least in this limit, we can see the scaling of these things. We can extract the scaling. So we just consider our partition function for a system of NT species. But of course, this NT is the number of species that are active at some temperature, so it depends with the temperature, but it's just free species. So it's just like the multiplication of the partition function for the one particle states over the factorial, and then the phase space or the momentum states per each of these NT species goes like TL to the d-1. This is, and then we also have like the average occupation number for, let's say, the average number of each species, which has to do with the number of momentum states that are available. This is just basic thermodynamics. I'm not doing anything special. I'm just putting an arbitrarily high number of species. But here we just see that this configuration, of course, as we know, recovers the volume scaling of the entity. Now the point is that because this number of active species, we can see that basically is like, roughly speaking, the number of species whose masses are below the temperature, because otherwise they are exponentially suppressed. There is, for those who are used to hackathon-like transitions, something like this, there is a caveat here, but for exponential degeneracies, but let me not go there. Just one can do it exactly the same. The analysis needs to be slightly refined, but the same approach.
2 weeks ago,
And the point,
You're trying to do the opposite.
the point is that, again, as I mentioned, we have this volume dependence, but as we said, when we just make the size of the box 1/L, then the entropy is basically scales with the number of species below temperature T. And as we said, as long as we keep the temperature low enough, this won't collapse. Now the question is, when would this collapse? Well, probably you can anticipate the answer, but it's indeed when we have T 1/L and the temperature approaches the species scale. Then NT approaches the number of species, and what we have here is a system that as we make it hotter and hotter, and we make the size of the box smaller and smaller, approaches the mass and the entropy of a black hole of that same size. And this lambda species is, again, nothing but the quantum gravity cutoff string scale, the higher dimensional Planck scale. So one recovers from this system of species, the volume scaling. Then one recovers a scaling with the number of active species, and in the limit, it has the same, well, there should be some stuff here, some boxes and so on, but it recovers the number of species at the entropy. And this actually is very reminiscent, you've heard about this, of this black hole string correspondence, which was originally proposed in these two papers and recently has had a lot of revival and lots of new arguments have been given in favor of this correspondence. So what I'm going to do here is review the basic argument in favor of this correspondence for strings, and then I'm going to try to generalize this to KK towers. And this is what I'm going to call this black hole tower correspondence. So the idea, as we were, like similar to what I was mentioning before, is that if you wanted to learn something about the entropy of a black hole in string theory, you have this relation between the string scale and the Planck scale equals 4 GS. GS is the string coupling. So you can start with a very large black hole at some value of GS, very semi-classical black hole. And now let me slowly make GS smaller and smaller and follow this guy along constant entropy lines. What would happen is that this guy, keep in mind that GS is basically like controlling the strength of gravitational interaction. So as I make it weaker and weaker, this guy, one can see that if I follow it along constant entropy lines, becomes smaller and smaller in string units. And at some point, one would expect that gravity becomes so weak that it's not able to keep the black hole a black hole. And then this is expected to transition to some string that then I can follow to a free string. Now, the key point is that if I can do this at constant entropy, I can give a microscopic interpretation for the entropy of this guy here, and this has the same entropy of this black hole. So this is giving an idea of how one could try to understand microscopic entropy of black holes in string theory. To be a bit more precise, one can do this in a bit more detail. And the key point is that indeed, if I consider this GS and I start with a black hole with some mass in string units, I can see what are the trajectories in constant entropy, which just go as 1 over GS. And then the question is, can I also match this entropy with that of a free string? Of course, for one point, this can always be done, but now the question is, here, these two systems would be expected to be equivalent if I can always choose to match the entropy or the mass. And because these two things have very different behaviors of entropy, like this is the area law, this is the entropy of the string that grows with its size, I can always choose to match one. But it is non-trivial that I can match the entropy and the mass. But it so happens that at around when this black hole becomes of the order of the string scale, as we were saying before, indeed, one can match both. And actually, this can happen not for only this black hole at this particular value of GS, but for an arbitrarily high number of black holes, they would always cross this line and they would have a free string that matches their entropy, and whose entropy actually goes as 1 over GS, which in the string case can be understood as this NT, number of species that I was telling you before. So one has this region with the black holes here, and one has this region with the free strings here, but non-trivially, one can match them at this point. Now, the key idea here is that one can play exactly the same game with a box of KK species and a black hole. Now, what is playing the role of my string coupling?
Okay. No. So this is
Before?
No, here it is always full since solution just up to some dimension.
Yeah, so
What happens
exactly. So
after?
what I'm doing here is the first matching only the mass and the entropy of the free string. This was the original argument for this, and indeed that worked for any dimension. What actually happens is that for the free string, the length, the typical size of the string, does not match by a factor of something, the one of the minimal black hole. Then what Horowitz and Polchinski thought was, okay, maybe what's happening is that because I'm not considering the self-gravitation of the string, when I'm considering it actually shrinks and the sizes match. This is what this solution is in D equals 4, this is what happens. In some other dimensions, this effect is still not enough to make the matching exact, but still what could happen is that the entropy, the black hole transitions to what they call an atypical string, which still has the same scaling of the entropy, so that is fine. And then above some dimension, I think it's 6, what happens is that you cannot, you find some strong back reaction, and then you cannot just use the leading interactions that they use. But along these lines, there's been a lot of recent works also from people here. There was a paper today, actually. So indeed, like what I'm doing is just the matching of the free string. If you consider the self-interacting string, things get a bit more messy. Still, the picture is that what can work seems to work. But the reason why I'm only staying at the free level is because for the box of KK states, which is what I want to extend my results here to, it actually turns out that the length also matches. So at the level of the KK species, I can simply do the free analysis to match mass, entropy, and typical size of my box. But indeed, what you're mentioning is just the difference between the self-gravitating solution and the non-self-gravitating solution. And the reason why the self-gravitating one, the Horowitz-Polchinski one, exists only up to some dimension is simply because they expand their solution around temperatures very close to the Hagedorn temperature. And they have some correction that goes like GS to some power that depends on the number of dimensions. And this power, this thing is negative or positive depending on the dimensions. So when it's negative, like you can really treat it in perturbation theory. Otherwise, you just get to some strong coupling. You cannot use that approximation, but the evidence from worksheet analysis and so on is that something could still work. But this is really crucial, as I said, for the string case. For the Kaluza-Klein case, which is the one that I also want to put here, this is not so crucial, even though we are also trying to work on the self-gravitating KK tower solution to clear a distance. Is that clear, more or less? Okay, so the only thing I want to highlight here is the fact that, as I was mentioning, if you play the exact same game with a box of KK species, now what is controlling the strength of your gravitational coupling is the volume. As you make the volume large, you're you're making your d-dimensional gravity weaker and weaker. And you can start also with a black hole here at some point, at some value of the volume, a very massive black hole. You follow it along constant entropy lines, which in this case happen to be like this for the dimensions. And then you see, as we saw before, that if you start with the box of particles, you can also match the entropy, the mass, and also the size of this thing. And this, as I mentioned, not only happens for one point, but actually the big picture is that it happens for a lot of, like, basically any black hole above some mass, but it happens at a different point. So this is the picture that I was saying, that at each point of the moduli space that I generally parameterize by phi, I have a minimal black hole that corresponds to a box of species with a different number of species, but I can still follow it and follow, and then in the free case, I can really understand the microscopic entropy of this box of species that then I can match with the black. Of course, everything I'm saying, let me emphasize, is at the order of these scalings, because of course the details of what happens here, we cannot know because it's strongly coupled gravity, and we can only do it in some other supersymmetric samples and so on. So now you could ask, what about other kinds of towers? And what you can do is turn this logic around. So I told you there's only, we only ever found KK towers or string-like towers. It turns out that actually, if you impose that this picture holds, I told you it works for stringy towers and KK towers. If you try to parameterize other degeneracies of different towers, it turns out that for polynomial degeneracies, which are like Kaluza-Klein-like, it works. For exponential ones, which is string-like, it works. For super exponential ones, you cannot treat it because you have a divergent canonical partition function. And for subpolynomial, it doesn't work either. So this goes along the direction of indeed finding a black hole evidence for the existence of only these two kinds of towers. Now, at this level, let me just clarify that even though this looks like a Kaluza-Klein tower, this looks like a string tower, we cannot exclude like a real P, which is the number of dimensions that they compactify, or anything in between. So we are basically bounding it by string-like states or Kaluza-Klein-like states. So let me just summarize this part and very quickly go to the last part. So what we did was, I was trying to argue what I was trying to tell you about these minimal black holes and so on, is that by studying configuration of species that do not collapse gravitationally and approach the maximum possible entropy, indeed one can get this volume scaling in one limit and this area scaling for black holes at this so-called correspondence point. And therefore, these towers for which we did explicitly, can give rise to this black hole tower correspondence, of which the black hole string correspondence is a particular case. And that indeed, if one actually turns the logic around and then sees for which kinds of towers I could have this correspondence, then it's only the polynomially polynomially degenerate ones and exponential ones along the lines of the emergent string conjecture. So let me very quickly go through the last part of the talk, which is about AdS distance conjecture, scale separation, and black hole transitions.
Can I ask a question?
Yes,
about-
yes.
So what is this, what is the punchline of this Swampland conjecture? Because you talked a lot about infinite distance and moduli space of quantum gravity, but this doesn't seem like it tells you much about the low energy physics.
So indeed, what we are finding, so what this is telling you, these large distance points are actually where you have arbitrarily good perturbative control and things like that. So basically, the way in which this is constraining, if you want, EFTs, is by telling you in these limits where you would expect your computations to actually be arbitrarily good, you run into a kind of dying cyber problem because you have something else that is breaking it for you. So you have this tower of states that is becoming arbitrary. So this would be like the punchline of the distance conjecture itself. Then I am trying to tell you as well that these two towers have to be of two very particular kinds, what means that you can resolve this problem by going to the theory that includes these new degrees of freedom. And actually you can treat this perfectly fine in this regime. And then what I was trying to tell you here is that along these limits, you can also try to understand what these minimal black holes do, and you can relate the entropy of precisely these states that become light with the entropy of these black holes along these weak coupling limits. Now, of course, if you tell me like, give me a concrete prediction from the distance conjecture for our universe right now, this was in the top left corner I was showing before, so the useless part. But it is very, I mean, it really tells us about a very universal pattern in weak coupling regimes in quantum gravity. And about the universal appearance of these towers of particles. How we can use this to really constrain phenomenology? I mean, this is one of the big questions that I think we all have. I mean, actually, a version of it is this AdS distance conjecture that I'm going to mention in a moment. But this, as I said, it goes more into there is more inputs, more assumptions needed, and then it can give you a little bit more. So actually, what this says, this distance conjecture, which is a generalization of this AdS distance conjecture, is that now you can consider a family of AdS vacua labeled by some cosmological constant. And if you can approach zero cosmological constant, this point is also at infinite distance, in the sense that also an infinite tower of states becomes light. And now this tower is related to the cosmological constant through a polynomial with this coefficient that is bounded from 1/2 to 1/e. And actually, what the strong version of the conjecture tells you that this is 1/2 for all supersymmetric stubs.
Sorry, M tower is defined as the fundamental scale that's defined.
Scale, let's say
Is
this.
M tower
It's like, for example, the mass gap in a Kaluza-Klein tower,
1 over R.
or the string scale exactly 1/r for a circle, the string scale for a tower of string excitations, and so on and so forth. Indeed. So, the known example of this tower is a Kaluza-Klein tower. And then, as I mentioned, the relation to scale separation is that it is a Kaluza-Klein tower 1/2, namely, for supersymmetric examples, one would never have scale separation. This is very much under debate. I'm not claiming this is far from proven. It might be right or not, but basically, let's say this strong version, but as I said, need more assumptions, is really telling you can never separate the scale of extra dimensions from the IR scale, if you want, in an AdS theory. Now, this, like using this for the zeta and so on and so forth, even the fact that in our universe, the cosmological constant is pretty small in Planck units, you could also argue that we are close to this infinite distance limit, that there could be towers and so on. But again, one can try to have scenarios motivated by these things, but at this point, we still need to understand them better to make them robust. That's my take. But still, you can take them, and the most natural thing would be to get something completely absurd, And the surprising thing to me is that you usually don't get something that absurd, but that's a different question.
Can you clarify a little bit the statement of the conjecture for me? So
Mhm.
do AdS solutions typically come in families or are they usually discrete?
I mean,
So
we
is
have a
that-
lot of solutions that come in families.
What's an
This
example
is
of a family?
AdS 5 crosses 5. Like you have some flags that you can tune. And
So
then
you count,
you
that's
take-
discrete, right? I mean, n is.
Yeah, no, sorry, yeah.
N is not a continuous parameter. then?
Indeed, they are always discrete, but you can have a limit in which as you make the n arbitrarily large, then the cosmological constant jump becomes smaller and smaller, and you approach 0. But indeed, this is like discrete families.
So
And then
in what sense is it a family? What's common to the elements of the family? Like, it's not a moduli, it's not, they don't all live in a moduli space of theories.
no, indeed, and that would be, let's say, if you could really define the notion of distance between two AdS theories in a family with different central charges, then you could actually give a precise notion of the underlying distance here. So let's
Well,
say
I'm just trying to understand if the statement is well posed. We don't even have, what is the definition of family to which this is supposed to apply?
you have some parameter that on which the AdS mass depends.
So I have two different solutions, just completely different solutions. I count them as a family.
You need an arbitrarily high number of these guys to approach this and indeed define this as a family. So a family of solutions, I really mean you have some parameter that you can make arbitrarily large.
But no relation between members of the family.
I mean, this is about the UV description of the, let's say at the level of the EFT, if you give me a family of solutions in the sense of I have some parameter on which the AdS scale depends that I can tune, and I can make this AdS go to 0 as I tune this parameter in something that basically in a way that approaches a continuum in this sense. For sure, this applies there. But I agree. Let's say I completely agree. Let's say this is based on a generalized notion of distance that indeed makes a continuous interpolation. Let's say uses a continuous distance and then evaluates it only at discrete
What
points.
is that distance?
If you only have the distance from kinetic terms, let's say for the distance in scalar field space, you were using the kinetic terms of scalars. In general, you can have the kinetic terms of any field, any form or any symmetric tensor. You can use that to define a metric in between different vacua. And this is what was used as a motivation for this in this paper. Like literally, you just take the kinetic terms, positively defined, use this as a metric, and in particular, you can do this for the AdS for conformal rescalings that change the AdS. To be very clear, that part, even here, I mean, this is again supported by examples, but that part has a sign mismatch that in this proposal was basically going to be taken care of by the UV completion. So the scaling is well defined, but the sign of the distance is not even well defined in this case.
So you say there's some notion of distance that we could talk about as the distance between SU2 super Yang mills and SU3 super Yang mills.
From this argument, from the AdS side, indeed, if you take the large n limit, this is the statement. But now this is the problem, that we actually don't have the field theory statement. Let's say when you do this let's say when you actually fix the cosmological constant and you just take moduli for fixed cosmological constant, you can do that. You have the sum logic of metric.
Sure, this I know.
But here,
But that's why I was asking about what you meant by a family.
and this is what we would need to actually have a properly defined notion of this distance in between configuration with different cosmological constants. So a family I can tell if I have the UV completion.
Why wouldn't you count them as a family? I mean, they are AdS with the same internal space as you're cleaning the same flags. It's very simple. Like, yes, your complaint could also apply to Minkowski with the modulus, right?
No, there's a continuous field whose better.
But still, right, that you move and
And
then.
here, it's more like there's a discrete flux that you.
Right, but it's the same flux that you're tuning, it's the same.
But
internal space.
there's no notion in which you can continuously connect them.
No.
Yeah, I
Right,
think
yeah.
place continuum is the n is not Bev of some field.
Yeah.
Like,
It's a discrete,
It's different.
it's not continuous. Like, let's say you can really define the family if you have the full UV description, and then you can really see what's the underlying description of this flux that you're changing, this parameter that if you have the string theory interpretation, then you can see it's some 5-form flux. And then I have a well-defined notion in in AdS 5 process 5 of taking the flux to infinity. And then this, let's say, I can give you examples of families. I cannot give you the full bottom-up definition of family in this sense. The closest I can go is there is some parameter that controls my cosmological constant that I can vary, that in the full UV theory may be quantized at the level of the EFT, can be just a parameter that I can vary and changes this, and then I can approach lambda AdS going to 0.
So changing the AdS over L string, or, the truth coupling is not the family.
So depends on which limit, let's say in AdS 5 process 5, it depends on indeed which limit you want to take. You have an actual modulus, which is this G string. You
No,
can,
not a string.
yeah, you have G string and you have the cosmological constant, then you have the tooth limit
I'm
in which,
talking specifically about AdS divided by L string,
Mhm.
which is the same as
yeah,
the truth coupling.
indeed. So
And that's an example of a family or no? It's a yes or no
So-
question.
in this point, in AdS 5 process 5, that is a family, indeed. But
Not
there,
to apologize to Clay about all the M stuff.
sorry.
So you have a family labeled by the continuous parameter AdS over L string,
So
which
if
corresponds in M equals 4 supreme mills to lambda, the truth
if-
coupling.
if
Yes
what
or no?
you have two directions. You have the direction in which you move the flux.
Continuous,
You have the direction in which you move GS. If what you're going is going to GS equals 0, even if you are accompanying it by some n that you change indeed as in the tooth limit. But what you're finding is that you go away from the regime of validity of the supergravity description, that is a mixed direction that can have this kind of tower, but also a tower associated to higher spin currents as you go to the free point in the CFT. So basically, let's say, what I'm saying actually, it's you can have moduli, where you do not change this, you can have only changing this and not changing any other moduli. What you're talking is a mixed direction.
What are you pointing to when you say this? You said changing this. What is, and you were pointing to something. What is the this?
Cosmological
Lambda
constant
AdS is a dimensionful quantity.
in Planck units. Cosmological constant in d-dimensional Planck units.
Oh, why are Planck? In the AdS 5 crosses 5, there are two
Mhm.
scales, L string and L Planck.
Indeed.
So why do you care so much about L Planck and not, for example, L string?
Because I can move in any direction that I want. What I'm saying is that this statement is meaningful if I move this in Planck units. You can move in string units, and the only thing you're having is, let's say, it's like if you had a modular space with two flat directions, you can move along one and you can have a KK tower, you can move along another one and you can have a weakly coupled string tower, you can move about some mixed direction, and then you can have a superposition of both. What I'm saying here is, if precisely for this to be valid, I must have a well-defined AdS in Planck units. If I go away from the limit in the EFT description where this is valid, namely if I make my AdS radius of the order of L string, I cannot use this description anymore, because there the tower that is relevant is the tower of higher spin operators in the free point of the CFT. If I am within the regime of validity of my supergravity description and I have well-defined notion of lambda AdS in Planck units, then I can talk about this tower. And I can have just mixtures of this. Is this? Yeah, I mean, I'm more than happy to keep discussing about that. But at the end of the day, it has to do with the endpoint. In this particular family, it has to do with the endpoint, the infinite distance that you're probing. If you're probing, indeed, radius of AdS over L string going to 0, or if you're proving if you're probing cosmological constant over Planck scale, you're going to see. But I think I'm basically out of time. So maybe I can just very, very quickly try to go through this. Okay. Okay. So let's say there's this AdS distance conjecture. And what we're trying to do is understand if there is some black hole inside into this range of parameters here, which bounds the maximum scale separation that you can have, which is 1/d, versus the minimum one. Now, to try to link this, you have to make you have to use another result, which is the idea that these towers, the scale of the towers, are in one-to-one correspondence with temperature, which neutral black holes undergo a thermodynamic transition that is not captured by the EFT itself. What do I mean by this? Again, in our two favorite examples, what I mean is take a black hole in a theory compatible with the circle, start making the circle bigger, the black hole wraps the circle. The moment these two sizes are of the same kind, I can have two possible uplifts of this. The one that wraps the circle and the one that is localized. The EFT, if I don't take into account the KK tower, let's say, only sees this shadow. But there is this other one that in the microcanonical ensemble dominates. And therefore there is a transition that is not seen by the EFT, and it happens at a scale that is actually MKK. Similarly for the string, as I mentioned before, there is the saddle, which would be the black hole if I forget about the fact that there's a string, and the dominant saddle. Now, the point is that by using that, one can relate the AdS scale with the black hole scale, because this one is related to the scale of the tower. And then the point is that for AdS black holes, sorry, I'm gonna rush a bit through this, but so that we can wrap up. In AdS black holes, there is a minimum and a maximum temperature at which in the microcanonical ensemble, the small black hole and radiation can coexist. And this range is precisely given by this 1/2 and 1/d. Therefore, small black holes in AdS, which are the analogs of the Schwarzschild ones in flat space, naturally encode this limit in which they can exist. And if there is a new transition that is not described by the EFT, it better be in the range where this small black hole can exist. Just very quickly, let me tell you that this, for example, in the case of the Gregory-Laflamme instability, one can indeed see that it's in this range, and it coincides with the Jeans temperature and the collapse temperature and so on when we have the maximal scale separation, and it also coincides with this one when we have no scale separation. This has been confirmed numerically and so on. And well, let me just summarize. So what I was trying to tell you is that indeed, not everything is allowed in quantum gravity, and to try to explore this, black holes can serve as a nice guide to try to guess what properties can be sensible properties of quantum gravity. And then what one has to do is to really take them and try to test them and compare them with full top-down examples and refine them if needed and so on. This is the part that we did not do here, but that we usually do. Then I try to connect this black hole string correspondence to a more general picture of this black hole tower correspondence, where I can understand these minimum black holes as the limiting behavior of boxes of species. And we saw that studying these configurations, we can recover the volume and the area scalings that the KK towers and string towers give rise to this kind of correspondence. But this is a non-trivial constraint that actually doesn't allow sub-polynomial or super exponential towers to work. And then I try to tell you how the relation between towers of light states and black hole instabilities, in cases, can be used in AdS to naturally encode this range. So that's it. Thank you very much.
Any questions?
Yes, there were already a few questions.
Okay, so there are no questions. Let's think Alvaro again.
Wait, I'm if I'm